Welcome everyone. Okay, so welcome everyone to this week's 1W-MINDS seminar. Today we have Professor John Harlim from Penn State University. Professor Harlim did his PhD at the University of Maryland in College Park. He was also a postdoc at NYU and an assistant professor at NC State prior to starting at Penn State. And I think you've been at Penn State for like 10 years now or so.
Right.
Yeah. And today he'll be talking about identifying missing dynamics with machine learning algorithms. Just so everyone knows, if you have any, this presentation is getting recorded, so but not the question and answer session at the end. So if you have any questions any clarifying questions that you want, or any questions you want to ask in the middle of the presentation, that's fine. Just remember this is getting recorded. And if you have something you want to ask that you don't want recorded, just wait till the end. And I guess with that, Professor Harlim, take it away.
Okay, thanks for the introduction. So let me just go to this topic. So I basically have somewhat three topics that I want to talk about in this aspect. First is I'll just discuss the closure formulations for this problem of missing dynamical systems. I'll give you, some flavor of what kind of theoretical convergence and numerical examples one can, deduce from this. And then the second piece is I'll apply this closure framework on a, reduced order modeling to identify basically statistics under perturbations of certain forcing on the dynamical systems. And then if time permits, then I'll discuss, under, which mathematical condition can one actually recover invariant or climatological statistics using the learning-based models. So let me go to the first part. So this problem let me basically simply denote it as follows. Suppose I have like two state variable, x and y, denoting resolved and unresolved variables. In real situation, basically your y is unknown. You might not even have a measure of that. What you have is a pretty much time series of x. And then let's say it just satisfies this discrete ergodic dynamical systems. Like I'm just describing this like a difference equations. I mean, this could be induced by certain discretizations of your spatiotemporal system if you wish. Okay, so I just want to highlight, the dynamical systems of X is usually known. Dynamical system of Y is unknown. So basically all of this functional G is pretty much unknown here. Now, what is the task here is that I would like to, reconstruct, an approximate dynamics basically to recover the fact that we are missing this function G that can actually track in many ways the evolutions of X, and in some cases also the statistical distributions of X. So this is happened to be, problem that occur in many applications. I'll just show you later, one or two instead of spending my time to talk about motivations. So now let me, deduce the study into two cases. So case one is basically sort of a setup that is laboratory setting, meaning it's a cheating. Like, why I say cheating? Because you typically don't have the time series of y. Y is very high dimensions, typically x, maybe something you can measure, So basically, but in order to understand the framework, let me just start with the fact that, let's say I give you x and y in your hand. And then once we understood that, then we are going to deduce, or to generalize this to the case where this is happening in reality, where you only have x time series of x. Of course, the operator f here, the dynamics operator f is known. So for instance, you can have some Navier-Stokes equations, and then you want to couple with certain type of, I don't know, maybe certain cloud condensation dynamics that you don't know, so those are typical example that I have in my mind. Okay. So In case one, suppose, I'll give you a very simple setting here that the dynamics is induced by a full discretizations of Euler-Maruyama on, like, let's say here's a SDE setting, okay, where you have, this is just the Euler-Maruyama discretizations. So sigma here is just denoted white noise, okay, just a standard discretizations of SDEs. Now, what I want to do here is nothing more than just to rewrite the thing, okay? So I want to rewrite a function g here, right? I rewrite it as a conditional expectations of, the Euler discretizations of the temporal derivative of y, conditioned to knowing x and y, okay? So this is merely just a rewriting. Since I'm lazy to keep tracking this ratio, then I just denote it by that, by y to the subscript delta, and you understood it's just that. Okay. Now, the fact that I rewrite it this way, then basically I can just replace my g, right? I'm just replacing my g with this. This is the part that you're unknown. Basically, everything in the red is unknown. Everything in the black is known, right? So usually, you're going to try to use a machine learning algorithm to estimate this unknown, okay? Let's say, suppose E with a subscript epsilon. So I didn't tell you what epsilon is, just parameter to denote perhaps error, okay? So perhaps perturbation, or this is your estimator of your G. So this is denoting the estimator of G. Then basically you can also define an estimator of the noise, right? Once you estimate the G here, which is the drift term of equation Y, then you use the residual to basically estimate what is the noise strength. This is typically what people are doing, okay? Now, assuming now that the dynamical system is ergodic, okay, one can basically identify this guy, this G here. The only reason why I write it as a conditional expectation of such is because this is actually an optimal solution of the following regression problem. So this is a regression problem where, you are trying to find a function that map x and y to the derivative, right? To the approximate derivative, right? It's like a supervised learning problem here. And you try to minimize this, under, G is all class of function that are L2 under the measure L2 mu. Mu is the invariant measure in this case. So basically, these connections, right, this way of rewriting is just saying that, hey, you can actually learn G by solving a supervised learning algorithm, such as to solve this particular least square regression formulations. And this is what, everybody's doing pretty much. So here, so far, I'm just being, being careful with the notation. Basically, I'm not doing anything yet, right? So what kind of convergence can we say about this? It's just the following, right? Basically, we have the first result is just the simple result is the following. Suppose if my estimator, is a consistent, okay, this is a consistent estimator here. You can estimate the G with variance error of order epsilon square. And if the original function f and g, which I replace here, are Lipschitz continuous under x and y, then, using the same initial conditions, you can prove that, you have like a pathwise convergence up to time t, and the error is scaling, epsilon, and then this is to the time t squared. So t is discrete time unit like integer, and delta is delta t, basically the step size, okay? So what this actually says is that if you want to predict up to this length, then it should be, inversely proportional to your learning error rate to the power of a half. So where the learning error is actually the learning of estimating this function g here. So the proof here is rather simple. You just basically, use the perturbation theory of ODE. There's nothing really fancy about this. And because everything is discrete, then you can sort of just deduce sort of discrete Gronwall lemma type. And, the constant here will have like Lipschitz constant, basically. Okay. So now, this is pretty benign at the moment, right? But let's give it a shot and put it on a very, very simple example. Okay. Say you have a Langevin dynamics here. So this is X It's just, so I write it in the Ito notation sense. So, but, you can think of y is just the velocity is like the xdt. And, y here I have a potential and then some noise. The potential, I'm going to pick like a quadratic functions. So it's just two-dimensional problem, really, really simple. So in this particular case, I'm just going to give you, time series of x and y I can, approximate from x in this case because it's just one dimension, but you don't have to. Now we will actually learn this whole thing that you don't know. So the g here is really, this potential minus y. We just have no idea what it is. So because this is a very low dimensional problem, right? Look, this is just 2D, right? Function of x and y, right? Then I don't need to use, very fancy neural network stuff. I could just use linear estimators. So in this case, we're just using, depending on which world you're in statistics, they call it kernel embedding of conditional distribution. I mean, depending what kernel you pick, if your kernel is Mercer with respect to polynomial types, then you're basically doing, a polynomial fit. So here, I just pick, Hermite polynomial fit on this function of x and y, okay? So there's nothing fancy about that. It's just depending on the language. So we did this, learn this whole things, basically doing statistical regression to learn the G, take the residual, as an estimator of sigmas, and then we get these approximations, and then you basically test it on new initial condition, and let's see what happened, right? So here's a new initial conditions. I think one of this, the green, I think was the truth. The estimator, the prediction of the estimator is the red, right? So you can see, what happened on the left is like if I use 50,000 training data, okay? To train this, I can track the trajectory up to a certain time, right? On the right-hand side, if I use tenfold of the data, I can track longer, right? I can make a prediction longer. So this is, you input new initial condition and you really do the testing on one things, right? And then what about that error bound that I was saying earlier, right? So let's say this G functions, is a Sobolev with a regularity beta where, I know from minimax theory, right? If this is the case, then basically the epsilon, the error bound for linear estimator is actually, bounded by this power, n to the minus beta over 2 beta plus d, in this case, 2-dimension. My function is super nice, so I'm just giving infinity even smooth. Then we expect, the time you can predict as good, is about epsilon to the minus a half, right? So epsilon to the minus a half is like n to the quarter in this case. Yeah, it's about 15. So it's about there, right? So that's what you expect. Of course, this is dirty. And on the right is just a bound, just an upper bound. So, it's a very conservative bound apparently. So numerically, it does a bit better, right? So on the right, but at least, you can say that, right? So then if you run this in a two-dimensional model, your trained model, like for a long, 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 long time, somehow, if you train it using more data, you can track, the invariant density. If you train it with less number of data, you don't even get it. So this is a question that I, haven't addressed so far. Why this is the case? What is the mathematical condition where you can actually track this invariant measure density? And on the right-hand side, it's just the autocorrelation function. So it's a 2-time statistics, okay? And there are a bunch of other measure people use to quantify, the mean exit time between the well and so on and so forth. So what I can say is like, basically with more data, you can track better, right? In this particular case, but I don't have a quantitative analysis on this yet at the moment, right? But that's pretty much is sort of the framework. So now, having that in mind, now we go to case 2. So in case 2 here, let's say I don't have the data of y. As I say, y could be very high dimension. I only have x, okay? So in this case, then basically, I think what's sensible is just to do the following. You're just saying like, okay, you take the dynamics that you're given is this. X is a function of X and Y, there is, you know this dynamics, but you think of them as a function of X and theta, where theta could be some variable that makes X and Y that can be identified. You want this theta to be something you can identify, right? Because think about it, if I don't look at it as a theta, if I look at it as this, even if you give an F, if I give you a time series of X, can you actually really identify the Y if Y is very high dimension? That's an ill-posed problem. So just to give you an example, right? Suppose, you have a nonlinear Schrodinger equation here. I just write down in Fourier truncations on the circle. So each Fourier mode of this NLS model can be written like this, right? You have a cubic interactions between all of these Fourier modes. Suppose now the resolve variable, the X is just the zeroth Fourier mode. So what I denote by Xi here is just U0, okay? So you look at the equation of U0, right? Which is precisely, U0 dot equal, discretization of this. Then you write down everything. You say, okay, this is as a function of resolve component. And then I have mixed term here, joined between all these higher Fourier modes. So now the same question I asked to you, right? If I give you a data set U0, you know these equations, can you identify all of these higher order Fourier modes? Of course, that's really brutal, right? Even if you can, then, so what? You probably don't need it if you just want to approximate the evolution of U0 or so on. So what you actually really need is, this is probably the identifiable unresolved variable. So this is an example of theta that depends on U0 as well as the higher order components. So just to give you a very simple example. So then basically the task is that I would like to actually learn, to close the system by concatenating the evolutions of X and also evolutions of theta. Because from X, I can now identify the time series of theta. So basically, the idea is just the following. All right. How do I do that first, right? Maybe, theoretically, we want to deduce the following framework. Let's say if I usually have a dynamical system fully X and Y like this, right? Let me write it as phi as just an operator that map this dynamics. It could be nonlinear function that map X, Y to one-time step. Suppose if I define S to be the Koopman operator on this Hilbert space, defined as S composed with the square integrable function, any square integrable function F, to be the compositions of F on the dynamics, right? Then let me also define a projection operator. So the task is like, now I'm trying to derive an evolution equation for X and theta, okay? So I want to project this, project these functions. So I define an orthogonal projection onto closed sets of function of X and theta. Now, by Dyson formula here, you can actually rewrite your iteration. So the power is iteration of this Koopman operator as follows, as a compositions of these summations, right? And then when it acts on these observables, this is become just a function of X and theta. Then you have, after a long derivation, but it's, pretty standard derivation that you can find in many textbooks, perhaps, especially for the continuous time. So I'm just deriving for the discrete time here. So you have a Markovian term, you have a non-Markovian term, you have orthogonal dynamics. So this is the standard discrete Mori-Zwanzig expansion on this. So then you can have a closed form of solutions of X and theta. So now the question is that, okay, how do I learn all this term, right? Basically, right? How do I close this? That's the real question in real application, right? Oh, I should mention Q is just the identity minus the orthogonal projection P. Now, there are several things that I should point out. It's like this representation, first of all, is not unique because it depends on the choice of P, okay? So there's no unique choice of P. For example, Zwanzig choose P to be conditional expectation like this. with respect to x, where x is a random variable that denoting the x0 at the time 0 and observable at the time 0. And then Mori choose these linear projections, like that. So they're not, then in this literature of Mori-Zwanzig, right, what people do is like basically they enforce one of these projection operator and then try to figure out what is this term, okay, by parametric form, like some approximation, usually using, let's say, rational function, this and that. So now my take is that, okay, because this P is not unique, and what I care about is just to find, I'm going to, at the end of the day, throw in a machine learning algorithm. So what if we just do this? Let's just choose a P that is completely super trivial. So which P am I going to choose? Okay, so I'm going to choose this based on the delay embedding theory. Okay, so let's say if I define a map, okay, this is define a delay coordinate map. Basically, the map of this snapshot of the solution at time 0 is basically sort of my observables, what I observe at time 0, what I observe at previous time. So it just basically, for instance, because I don't observe x and y, right? I observe only some observations. In this case, is x and theta. That's what I will observe. So you basically look at snapshot at different time, right, of your observable, which is, I call it function pi here. Now the delay embedding theory is saying the following fact. Under mild assumption on your observable functions and your flow map f and g here, right, then it states that if you choose this delay time m large enough, okay, so this map here, zm, this delay coordinate map, is indeed a homeomorphism between the support of your manifold and basically your invariant measure of the dynamical system. Oh, sorry, the support of your invariant measure and this tuple r to the 2nx, each dimension here to the power of m. So tuple of these snapshots, basically. What is this supposed to mean is the following, right? This means like the Borel sigma algebra of your M here is just equivalent to sigma algebra generated by this, snapshots, this delay coordinate map. So then, what if I now choose my P to be conditional expectation given that of whatever I want to swallow, or whatever random variable I want to swallow, given seeing some snapshot in the past. So what I'm saying is just the following. Suppose if I take P, I acting on this pi t plus 1, which I define as, this is just basically a notation for random variables, random variables corresponding to pi, because usually, right, little x is a realization, capital X is like the random variable corresponding to realizations. So I'm just using the notations that if I take that, so this is basically just the Koopman operator acting on these functions, right? I take that. That means if I take the conditional expectations of what will happen at time t plus 1 on this observable, given I know the history, just because, this Borel sigma algebra is tell you everything, that means, there's no more random here. That means it's like you've seen enough movie so that basically nothing is secret. Your answer should be exactly just, the functions, okay? Because it's like you're actually watching enough movie and you get reminded, I've seen enough, so I know what's gonna happen. So at the end of the day, right, why I say this is a very, very simple projection operator, because you look at this projection operator, I want to highlight, it's an identity operator. So I choose an identity operator. So P acting on this is just identity, right? I'm not doing anything. Then, if P is identity, anything involved the Q, identity minus P, those are all crossed out. So basically, but remember, right, my identity operator itself is already non-Markovian, because this depends on the snapshot at the end, right? So what I call the Markovian here itself is already becoming a non-Markovian, right? So if you use this principle, right, and then you basically just derive this carefully, then basically you can rewrite your dynamical system, which is originally a function of, say, where is it? X and Y, right? This is the original function of X and Y. You can rewrite them as a function of X and theta, okay? So what am I doing? I'm just rewriting. I'm not doing mathematics even here, right? I'm just doing, so I'm not even approximating Mori-Zwanzig. I'm just using Mori-Zwanzig like a trivial matter here as to rewrite what am I supposed to estimate. So my true dynamical system now is evolutions of X and theta. This is the object that you're supposed to approximate. It's just this operator here, right? Now, what is important by rewriting this as a conditional expectation is like, again, we can identify this conditional expectation by solving this supervised learning algorithm. So basically, at the end of the day, is that, this is your closure model where you're going to learn this G0 here by solving a machine learning algorithm here. So the point is like, well, which hypothesis class you're choosing, that will matter, of course, right? Say if VM is choosing based on, who knows, maybe just polynomials, then it will only give you a good estimator if this is a low dimensional problem. For high dimensional problem, you might need neural networks or other things, which I'm going to show you some example here. Then what you can say in this case is the following, right? Suppose, the full dynamics now under this Haken delay embedding theory works, you can rewrite it as such. That's your full dynamics that you're trying to estimate. Here I just make it simple. So I define Z to be a function of X and theta, right? Now, of course, this could be a very high dimensional system, right? Because this could be M times 2 times, depending on what the size of X, right? Consider now you approximate this model. So this is your approximation using your supervised learning algorithm. And if this is also a consistent estimator in the sense the variance is order epsilon squared, and that's just Gaussian noise. I included just to, to ensure, like, let's say if the hypothesis space that you choose to approximate this is not large enough, then you can account for the residual, but sometimes we don't even need it, okay? And then also if PS is uniformly bounded, P acting on the Koopman operator, which is basically saying if this G is actually Lipschitz continuous with respect to X and theta, then under the same initial condition, you can deduce this error bound too, okay? So now, of course, instead of polynomial in A, so now it's like, sorry, polynomial in T, but now it's exponential in A. So it's rather useless bound, but it's bounded. At least you can bound this, right? The reason why I said it's a little rather useless bound for practical is because, I mean, we don't have any more assumption on anything else, right? This is just basically come up from the Gronwall, and the A is actually this independent constant is depending on a lot of the Lipschitz constant here, right? So I don't have any more structure in here. I suspect that, this is sort of an open problem that I don't, I suspect this A might be something corresponding to Lyapunov exponent, but, that's just my suspicion, at least for the deterministic system, okay? So let me try this, okay? Let me try this algorithm a second. So let me try it on simple problem. Let's say spatiotemporal chaos, Kuramoto-Sivashinsky equations here, right? So in this case, this is discretizations in each Fourier modes. You have, let's see, okay, the true dynamics, right? So numerically, the true trajectory, I constructed using 48 Fourier modes. And then let me just resolve the first 6 Fourier modes. So my X there, initially on my notation X, and we have 6, okay? Six dimension, complex, so it's a 12 dimensional real value number, okay? So that's the first 6 equation we know. So this is that. And then the theta here is basically, you can guess, this is just basically the summation that is not in here. So the summation combination with other index, right? So now given a time series of the first 6 components, you can of course extract the time series of theta by doing some discretizations on V, right? Now I concatenate this, like I say, with these equations here, where this is just non-Markovian functions that depends on v at the previous time and theta at the previous time. Okay, and this is coming out from. So before we did this, actually we saw a bunch of paper. They're trying to just depend on v, so no theta, right? We saw a lot of other paper doing that, but then based on this Mori-Zwanzig argument, it should also depends on memory of theta. Now here, right, instead of trying to derive this parametrically, right, now I gave up. I just say, just put neural networks. And one of my collaborator, Hai Chao Yang, his student is working on this, and Wei Liang. So they say, why don't you just use this a type of recurrent neural network? So by the way, just to tell you how difficult it was, this problem, it was, at least for many years, I didn't think, it's that easy unless you can deduce some parametric model. You think about this is actually quite high dimensional function that you're trying to approximate, right? See, this is like, this is output is like 12 dimension because it's the same like that, right? Now the input here, you can see is 12. So if I put m is 20, just 20 like to the back, this is already 480 dimensional functions, right? 12 by 20, that's 240. And then there are two of this, right? So 480 dimensional functions. So this is, I thought initially like, how you're never gonna get this, right? So we just train this, right? They train it. I didn't do the numerics. So they train it and then they test it. So one of this is actually, this is showing a panel, I cannot remember A or B. One of this is the truth. The other is the predictions under new initial conditions. So x-axis is just the spatiotemporal and y-axis time is going up. So you can see, up to a certain time, I think they're doing quite okay. They're quite behaving quite well, right? And then here also we show, let's say, what about the evolution of the first Fourier modes? There are many in the paper. We report everything. But here, for conciseness, this is just, up to certain time, let's say about 40, the Fourier modes, they are quite okay. And then they start to deviate, right? As you expected. Now, if you also run this model for a long time, right? Then somehow you can approximate the autocorrelation functions, the cross-correlation function between different modes. This is sort of empirical estimation of the density of the first, I cannot remember, first Fourier modes here. And then this is the energy spectrum of the 6 Fourier modes that you resolve. You can actually recover these statistics very long. So, we thought, okay, that's quite interesting, right? So it's just a very simple method, right? All the method was just, you take whatever dynamics, you embed it with, something that you just learn by memory and the back, right? So that's the first part of this talk. So now having this, so we thought like, well, let's, apply this on something a little bit difficult than that problem, right? So you'll see in what sense this is a little bit more difficult. So I was, aware of this statistical closure problem because due to, my connection with at Quran, working with Andy Maida before, and then they were doing all this. So I was thinking maybe we can try to apply to one of the problem that he was working on at the time. So here's the thing. It's like, let's just consider the following. So this is just basically I call statistical closure problem is induced from many problem in turbulent dynamical systems. But here, it doesn't necessarily have to be turbulent. It's just any nonlinear dynamical system is okay, but I will concentrate on this class. Say this is a SDE. You can ignore this noise if you don't want to. You can think this is just an ODE. L and D, this is just a linear operator. D usually, you can think of this ODE is induced by certain discretizations of PDE, if you wish, like discretizations of, advection, nonlinear advection diffusion, if you want. So D could be, dissipations. L could be something like skew symmetric or other linear operator that you like. B is a bilinear operator usually induced by nonlinear advections, but here I just put it generic, whatever B. Usually they, in the fluid community, they like it to so that is divergence free fluid, then u dot bu equal to 0 or this and that, but we don't need it here. It's just, but I just think, okay, let's try it on this problem. And usually what they're interested on this benign quadratic ODE, okay, if without the noise, is that let's try to find the following decompositions. So you decompose the vector field here, okay, which also depends on stochastic noise. If there's a noise, or maybe the noise induced by uncertainty of initial conditions, if you don't have this, then you want to basically decompose this into a mean field plus some perturbations, okay? And if you're lucky, you can find some coordinate for the perturbation here, then you can decompose them, and Zi is just, the sort of the coordinate in this EI. Okay, then what one usually do is like you plug in this into the dynamical systems, and then you can try to find the equation for the mean, equation for the fluctuation here. Okay, and basically try to come up with a reduced equation for this. But here's a complication in this particular case. It's just due to the quadratic interactions here. So, for the mean equation, you have this contribution of this R, which is basically the covariance of the fluctuations. Whereas the fluctuation equation, it is actually induced by, here's a conditionally linear operator A. So why I say conditionally linear is like A is like a linear, except when you froze the U bar, right? U bar is like your mean. So conditional to knowing a certain mean, then they are linear. But this matrix here, because U bar is changing in time, there's no guarantee this matrix could be, negative definite. Sometimes it could, go up and down. But whatever that is, if this equation, satisfies some conservations, then they're supposed to not blow up. They're fine, right? So this is, standard problem in the turbulence community is like, they took the Navier-Stokes, then U bar is like Reynolds averaging, they deduce this. And you can see, if I try to actually close the Z, it depends on the higher order moments here. If I try to close this, I could never close it, right? So the equation, if I take Zi here and then, take expectation, then you have covariance will depends on the third order moment. You write the third order moment, it become equation fourth order moment, so on and so forth, right? So this is like, tale of never ending. And then what crazy is like, if U bar is n dimension, then the covariance is n squared, okay? N times n. And then the cubic, third moment n times n times n. So it's just, quite a beast of problem to close, right? So basically, one way to lead to a reduced order model is you just try to predict, to some leading mean and variance energy spectrum, to try to reduce the number of modes here. So instead of this is very high dimension, perhaps in the right coordinate, this become, it has like a peak energy spectrum, okay? So now, for this problem, right, what is the goal actually? The main task is that I want to predict the evolutions of the mean and perhaps the covariance, okay? So this is a function of time here. When the dynamical systems now is perturbed, okay? Or when initial condition is changed. So this is sort of a problem related to perhaps, climate change problem or so what, if you change you induce certain forcing, then you want to see how the statistical change in time, and then also characterize the uncertainty of changes in time. So that's the task that we want to do this. Now, to avoid Monte Carlo simulation of the full system, of course, if you want to do this brutally, you just take the full system, right? You put a forcing, you run Monte Carlo on this, right? And then you compute and see how they change the statistics from your reference, forcing, for instance, right? But that requires brutal computation. So what we would like ideally is like, this is the problem I was introduced to, is like, can we close this actually? Can we just deduce this reduced dynamical systems here? So I want to close this, okay? This error here, right? Once you do the reduction, where's this error come from on the first equation? At least it's like, look, this is summation over the full thing, but now I just sum over just some reduced indices, right? So then I induce some error. And also the Z, I also induce, some error because you have interaction of higher order moments that you don't know how to resolve any of this, right? So it comes, naturally, this is sort of like a missing dynamical systems that we don't know. So what I would like to do is like, I want to use the framework on the first part of the talk and then just put it here, embed it here, right? But there's a problem here. The problem is the following. If we write the covariance equations, right? Basically, this is Riccati type, right? Then, I know this is n square if it's non-homogeneous, right? Unless if a homogeneous dynamics, meaning, every mode behaving the same, then this is just diagonal equations. Then basically, I cannot just, put any random neural network in here. Because if I do that on the noise here, right? Then this might explode because the reason is because as I told you, there's no guarantee this guy is going to be negative definite. So it's actually very hard to do this, right? So, we stumble upon this for a long time, and then DG is Andy Meidel last student, I believe. So he came up with this idea. He said, okay, let's just parameterize this. This is the trick he learned from Andy, I suppose. Let's just do this, like put a damping and noise. But instead of doing like a standard parameterizations on D and sigma, let's just identify D and sigma using neural networks. So it's like you embedded certain parameterization, and you want to embed this so that basically the flux is actually consistent with the true flux. This is not easy to be done too, actually, in practice. Okay, if this is all full non-diagonal covariance, it's actually not easy to be done. But he managed to do in one way, these things. So there's detail in the papers, which, at this point I don't know, because he is the one who implemented this technique. So basically what we did was we just employ the recurrent neural network, the LSTM, to close this theta, D, and sigma. So that's what we were trying to do in this case. I think there should be a better approach to parameterize this at the moment. I am actually talking to a lot of people and trying to fish a better idea how to parameterize. If any of you have some idea how to parameterize this better than what we did here, please talk to me. I'm very interested on how to do this actually, right? So now let me show you what happened in example, right? So suppose we just try this on very simple example, like 40-dimensional systems. I modified this equation so that the damping is not constant in certain case to make it non-homogeneous statistics. And the forcing F, could depend on time. So basically, I will, depending on, okay, we'll train the model on various constant forcing. For instance, forcing 8.8, or so, just constant forcing. We train the model using time series of statistics from this constant forcing. Now, if the forcing is changed, then the energy spectrum also kind of change, like they behave differently. Okay, the larger the F, the more chaotic is the system actually. Now, once we train all of that, actually, we tested on the following constant, non-constant forcing, continuous time forcing. So we draw, this is like an example, you ramp up, right? You test it when you learn the dynamics, the statistical dynamics, then now we force it using this type of forcing, or maybe some periodic. And then we want to see how this behave. Does it actually predict this statistical changes, right? So that's the idea here. So now there's another difficulty here. It's like, think about it, right? I am trying to find a statistical closure. So what am I supposed to fit? I'm supposed to fit the mean and the variance statistics because that's what I want to learn, right? It's not fitting the trajectory, okay? Trajectory is easy to get. So that means it's like, this is sort of a training data. You don't have that many training data. Like, why? Let's say, each of this curve, right? I have to run Monte Carlo simulation pre-training just to prepare this time series for certain forcing perturbation. Then the forcing, then the dynamics, like this, because we use constant forcing, then the mean statistics of the dynamics will go to equilibrate. And then also, the variance, right? They will just go to equilibrate. So you don't have, let's say, the luxury of if you are trying to train the trajectories just keep fluctuating. But for statistics like this, they basically decay after decorrelation time, right? So this is our training data. Each curve here, you Monte Carlo, retrain this, right? Then this is sort of your perturbations on different F, right? So here's your mean statistical response. Once you train this, you test them. So here's our testing, for instance, total mean, total variance. For the homogeneous case, when you ramp up the forcing, can you actually predict this truth, right? Or when you put now different oscillations on the forcing, can you actually predict this, right? So we got this relatively okay for homogeneous case. Remember, homogeneous case is the easiest one. Why is the easiest one? It's because this equation become diagonal, and this equation here becomes scalar, very homogeneous in space. Okay. Now, for the non-homogeneous, then it's complicated. Then this equation, is actually a vectors, and yeah, that the R is non-diagonal. The non-homogeneous case, we also train using various inhomogeneous forcing and inhomogeneous damping. Okay, and then basically so here I just show you some result. If you under new initial conditions, then you can predict. Here's the U bar of the zero mode, so the mean, and then U bar of different spatial resolutions, and then also trace of the variance. You can sort of predict this. And this is prediction under different external forcing. So let's say if on the top, I just do different forcing, say F1, F2, F3. I think this is on the lower, on the top, this is different forcing. Then you can sort of predict this. So relatively okay, but so there's a lot of details hidden in this, right? So I believe, I've gone through like about 50 minutes here, right? So yeah, I know I have a third topic, but I could just stop if you want me to stop.
Long as I don't know, do you want to give him a few more minutes to cover the third topic?
Okay.
Yeah.
Okay.
Okay.
So the third topic is actually stimulated by this annoying fact that once you learn the dynamical system and then you run it a very long time, sometimes you can predict this invariant density or the autocorrelation functions, right? So I was, having a hard time to understand how come sometimes we got it, sometimes we don't, and there are many, many papers, not only us, actually, many, many papers. When they got it, they declare victory. They use this metric as like to show in the paper, like, look, we got all this, right? So then basically I was drawn to this, trying to understand how to actually study this, right? So here's a sort of a sketch of an idea, maybe this, right? So let's say if you have a dynamical system, abstractly, it does suppose it possess the invariant statistics, let's say the invariant measure, the statistics, 1-point statistics. So if f is x, this is just mean. If f is x squared, this is variance. And then let's say 2-point statistics. Let's say it possess all this. Then basically, if we want to study this carefully, right, we should say like, wait a second, we don't have a continuous time series in our hand, right? You never have xt. You don't know the true solution. What you have, most likely, is just some numerical discretizations of this. If you're lucky, there's no subject to other noise, right? You just have perhaps, a time series subject to some quadrature error, right? So this is a Markov chain that you have. And then you if you're lucky enough, like you have to ponder that whether this Markov chain itself is ergodic. If it does, has invariant measure, question one is like, how far are they from the true invariant measure that you're trying to attain or approximate, right? So basically what I'm asking here is like the quality of your training data. That's number one, right? Has to be in there because it should affect the error. Why? Because when we are now employing machine learning to learn this a function b, which I denoted by b epsilon here, you are not using x. You're using this discrete data to learn, right? Now you apply the machine learning. So the question two is like, okay, now you have the model. Whether this new model here that you get, your approximate model, does it have invariant measure? Does it have the statistics? If it does, how do they converge to the true invariant measure and so on? So that's the questions to question three. Question three actually is like, if I use specific machine learning method, right, can I characterize the error bound on this? So those are the three main questions that we're trying to address here. So just, like I say, how good is the available training data? The second is like, can you approximate, the invariant statistics? So if so, right, let's say, your learning error is epsilon, learning error b under some metric. So of course, which topology is correct to do this? So we are actually using perturbation theory of Markov chain by Rudolph and Swasser. And then for 2-point statistics, we're using linear response theory to deduce this. And then once you have all of this, basically, if you apply a specific machine learning algorithm and epsilon characterize your generalization error, then how to identify epsilon in terms of training data, dimension, complexity, so on and so forth. So basically, that's the more or less the gist of this. So we have for Ito diffusion, so I'm not going to go through detail on this. So here's sort of the main result that we have is just the following. For Ito diffusion, right, with constant coefficients, so the equation is this, right? This is the equations. So I'm trying to learn B using the regression, use the residual to do this, right? And then what happened is, in this case, why I only study this is because it has a quality, the quality of training of data is there. Somebody already proved this. Mattingly, Stewart, Higham already proved this. If you use Euler-Maruyama, question one is answered. So then I can actually train using this data, right? So now you just do your machine learning on this. This is your label, again, to learn this function B, right? Let me, sort of write down this, just tell you the result, right? So basically, here's the gist. Is like, if your estimator is globally Lipschitz, okay, and then also you have a consistent estimator in this sense, okay? So this is vector, so this is stronger than L2, of course, but you allow it to be linear growth because, okay, you take square root of this is order epsilon, but then there's a growth here. You allow the error to have linear growth, right? Then you can approximate the invariant statistics here, by this expectation of this Markov chain for initial condition X. You can bound it on the right-hand side up to epsilon. B is just Lyapunov exponent. Sorry, I ignore all the detail. If I have given 20 more minutes, then I can say it more carefully, but it's all right. Right. So basically, what I'm just trying to tell you is like, if you have an estimator that is consistent of order epsilon, then the statistics is also linearly scaled on the order of epsilon under this hypothesis. So this is, we can prove this for SDEs for something very simple, right? So there are a bunch of remarks here. Let me, I have deduced error bounds also if you use ReLU, but let me not even go to that. It's just useless at the moment, right? Right. So basically, basically what the takeout from this is the following. You should actually prepare your hypothesis space very carefully. So meaning you want to approximate B, you suppose, if you know how to characterize the B using a much better hypothesis space. So for instance, in these theories like Lipschitz, and then then you might have actually consistency, which is this is why we need the physicists. So it's not a blind machine learning, right? Then of course additional bias, then there's also additional bias to the inconsistency of learning model. What I mean is the following, right? Say your SDE, you discretize it using method A. your learning, you write your learning algorithm, meaning this is your learning algorithm here, right? This is, I use Euler here. It's not method A or method one. So then you induce bias, right? Your data come from a discretization of method one, but your learning algorithm is written in terms of discretization of two, then you have another bias, right? And you don't know that, that's the hard part, right? So then that'll be open questions. And then the hard part is actually deterministic systems. Why deterministic system is harder? I mean, you can think about it in very simplistic way. It's like, say if you learn the dynamical systems where the equation is very simple, even on the right hand side. I don't know, let's just say ax squared, right? Parameter a is small, right? And then you learn that, right? Somehow your a is supposed to be positive, but then you learn that you're messed up. You messed up negative or something, right? Then your solution, actually, what I want to say is like bifurcate, basically, right? So under small error, it could, your total solution structural change. Then that's very hard, I think, for deterministic system. And I believe actually that's the main question in linear response theory for deterministic dynamics, is like, when does linear response exist, meaning under mild perturbation, whether you can approximate the invariant measure, right? Now, this is okay. I'll say anything. So let me close the talk. I mainly, first part of the talk is this paper. Before this paper, before I understood machine learning can do something for me, I was doing simple machine learning using kernels. So I already sort of formulated here. And there's some aspect of this work that actually contribute. So the first part of the talk, I would say, sort of composition of these three. The second part of the talk, like I say, this is done mainly by Di Chi. This is the two papers. The third part of the talk, which I didn't have time to say much, is basically done by my former student He Chang here. So this is this paper. So let me just stop. I mean, this last paper is just some other thing. I shouldn't even include it here. Maybe it's okay.
Um,